Hello, welcome. In this short video, I will derive the probability density function of the sample mean. That is, I want to show that the probability distribution of sample mean x bar is a normal distribution. The mean equal to the true value of the parameter, and the variance equal to sigma square over n. So, given the model x of I is equal to a plus a random component w of I, where w of I has a probability distribution function with mean equal to 0 and variance equal to sigma square, then the sample mean that basically estimates the constant a, x bar equal to 1 by n summation I equal to 1 to n xi. That is, the sample mean is the minimum variance unbiased estimator of the constant a. Now we want to derive that its probability distribution is a Gaussian distribution with mean equal to a and variance equal to sigma square over n. So from this definition we can clearly see that the expectation of the sample mean, that is expectation of x bar, is equal to the constant a, and the variance of x bar, that is the sample mean, is equal to sigma square over n. These results are derived in previous videos. So now by using the central limit theorem, we know that the variable z, a new random variable defined as x bar minus a over square root of sigma square by n, that is this transformation, that is this new variable defined by this transformation, follows a normal distribution with mean equal to 0 and variance equal to 1. So this is a central limit theorem. This is especially valid for large values of n. To derive the probability distribution of the sample mean, that is x bar, we start with its CDF, that is probability of x bar less than a, which is equal to the CDF at the value a. So this probability can be, now by using this definition, we can write that x bar is equal to z times square root of sigma square over n plus a. So by using this transformation, probability of x bar less than a becomes probability of a plus z times square root of sigma square over n is less than a, which is again equal to probability of, by subtracting a on both sides and dividing with square root of sigma square over n, we have z less than a minus a divided by square root of sigma square over n. And since we know that probability distribution of z is a normal distribution with mean equal to 0 and variance equal to 1, so we can derive the probability distribution of x bar. Therefore, the probability density of x bar at value a is equal to the derivative of this CDF, that is derivative with respect to a of the CDF, and the CDF of the x bar is equal to the probability of z less than a minus a by square root of sigma square over n of this probability. But this is equal to the probability or the CDF of the random variable z at the value a minus a by square root of sigma square over n. So therefore the probability density function fx bar of a is equal to the derivative of this CDF, that is fz of a minus a by sigma square over n, square root of sigma square over n, and this is clearly equal to 1 by square root of sigma square over n multiplied by the PDF of z at this value, that is fz at a minus a by square root of sigma square over n, and the probability density function of z is a Gaussian density. So we have 1 by square root of sigma square over n into 1 by square root of 2 pi multiplied by 1, variance corresponding to the random variable z multiplied by exponential of minus a whole square divided by 2 times sigma square over n. And clearly this can be seen as square root of 2 pi multiplied by sigma square over n into exponential of minus 1 by 2 a minus a whole square over sigma square by n. That is a Gaussian density with mean equal to the constant a and variance equal to sigma square over n. Therefore, the probability distribution of the sample mean x bar is a normal distribution with mean equal to A and variance equal to sigma square over n. Thus, by using the central limit theorem, we can derive the probability distribution of the sample mean. Thanks for watching.